In lesson 2-3, we're going to be talking about equations with variables on both sides of the equation. So, the main thing that you need to think about is that you're going to use the same exact rules that you've already been using, but you need to make sure that you get the variable to one side of the equation, and you're going to do that using the inverse operations that you've been using. So I'm just going to go ahead and start with the example, and then we'll go write stuff on the left. Example 1 says to solve 6x plus 3 equals 8x subtracting 21. And this kind of goes along with why I've been telling you to draw that line out of the equal sign, because what you don't want to accidentally do here, these are like terms and you're used to combining like terms now, but you were only combining like terms that were on this side or this side. Now you need to combine like terms, but they're going across. And if they're crossing that line or that equal sign, then you need to think inverse operation. This is a positive 6x. If I want to move it to the other side and make it cancel over here, I need to subtract 6x. And if I subtract 6x here, I have to subtract it there. Same thing, if I wanted to move 8x over, 8x, I would subtract it to both sides. Notice when you move the 8, you're going to end up with a negative answer with your x. When you move the 6, you're going to end up with a positive answer. It's completely up to you. There isn't a right or a wrong. You can move either or. The pattern I tend to follow is I like to try to keep it positive if I can. So I don't worry about which side the variable ends up on. I just worry about, is there a way for me to at least start with a positive right there? Doesn't mean my answer will end up positive, but it at least gives me a start with a positive number so I don't have to think about it as much. So again, either or works, but you're going to use inverse operations to get the variable to one side. So subtract 6x from both sides, or you can think of that as adding a negative 6. 6x minus 6x, remember, x's here are still coming down in the sense, but what is 6 minus 6? It's 0, and 0 times x is going to be 0, because 0 times anything is 0. So that whole term cancels, and you wanted to do that. Now you just have a positive 3 left on the left side. You combine your like terms here. 8 minus 6 is 2x, subtracting 21. And now you do exactly what we've been doing. So now you're trying to isolate this variable. The variable's on the right, so I want to move everything else that's on the right away from it. So first thing I would do is move the negative 21 since it's subtracting from the x. So opposite or inverse operation is to add 21. I end up with 24 equals 2x. And I'm still trying to get this x alone right here. 2 is multiplying to x, so I'm going to divide both sides by 2. I end up with 12 equals x. And then again, the way that you can check it is you plug in 12 for x at each of these, and you see if the equation balances out. And for notes, I'm not going to do that because I already know that this is correct, but you always want to check that on your homework and on your tests. Alright, let's write a little bit on the left. So you're going to follow the same steps as having the variable on one side. Except you need to move one term with the variable to the other side first. You use inverse operations. So that should be your first step every time. And then once you have the variable to one side, then you're following all the rules that we've followed before. Okay, hit pause and finish writing that if you need to. I'm going to go ahead and move on to example 2. Example 2 is a word problem. You do need to understand these types of word problems. You're going to see them throughout this whole chapter, and you'll see them again later this year. So it talks about cost the same. When the cost is the same, or it might talk about breaking even. So maybe when a business breaks even before they start to make money. Anything like that where it's talking about when something is going to balance out. And we're going to look at that and talk about how you want to set those equations up. So this is example 2. You can buy skates for $40, and you do want to write this down. Or you can rent some. Either way, you must rent safety equipment. How many hours must you skate before the cost of buying skates or of buying and renting are the same? And then they're going to tell you that the rental equipment for skates and equipment is $3.50 an hour, $3.50 an hour. And just equipment is $1.50 an hour. So this is actually really important. This is a concept that you'll use a lot in life, even when you don't realize you're using algebra, because we think about things like this all the time. Like when there's a deal, if you buy this many of something, you get it for this much, and you have to stop and you have to think, okay, well, when is it going to be worth that? Or if anyone here has a cell phone, when your parents go to look at your cell phone plan, they're looking at what the cheapest cell phone plan is going to be based on how much you use. That ties in with this idea. When am I going to break even before I start paying more? So you don't have to write this in your notes, but I'm going to go ahead and draw something really quickly that I just want you to look at. Let's say that you are looking at a new cell phone company, and we've got the blue company who says, we're just going to charge you 30 cents a minute. And then you have the green company that says, we're going to charge you $1 per month plus 30 or 10 cents for every minute. So notice the minutes here are a lot cheaper, but you have to start with paying $1. And this is a very, very basic, small idea, but I just want you to get a feel for how this works, because it can obviously be a lot more expensive and applied to more expensive things. So what we're looking at with the blue company is, if we're talking about minutes here, at 0 we have 0 minutes, and then let's say that this is 30 cents, and so we go, if we're talking about this as 0.30, and then 0.60, and then 0.90, and then $1.20, $1.50. Okay, we'll just go up to that just to see. Actually, we can go to $1.80 because that'll be better to see. Okay, so at 1 minute I pay 30 cents. At 2 minutes I pay 60. At 3 I pay 90. At 4 I pay 120. At 5 150. And at 6 180. So this would be if you were to, the approximate, if you were to go ahead and use this plan. Now, if you know that you use your phone a lot, you might be interested in looking for something like this. So notice that at 0 minutes, you're already paying $1, which starts right there. So if you were to never use your phone, then obviously the blue company is a lot better to go with. But now what you're looking at is from here, at 1 minute, you're only going to there. And at 2 minutes, you're going to here. 3 minutes, 4 minutes, and I might be off a little, but it gives you the general idea. 5 minutes, 6 minutes, 7 minutes, 8 minutes. What I want you to think about now is, if you were only talking for 2 minutes, which company would be better? 3 minutes, which company would be better? 4 minutes. Just stop and think about that and look at those. And then I want you to stop and think about, when would it be better to use the green company? So remember, here we're counting by minutes. So this is 2 minutes, 4 minutes, 6 minutes, 8 minutes, and I know my graph isn't perfect, but we can look at the general idea here. So hopefully most of you noticed that after this, after about 6 minutes, it was cheaper to use the green company. What we're going to be looking for in all of these problems is this right there. When it's the same. When you're not losing money, making money, and it can tie into so many different things. It can tie into you as a consumer who's looking for the best plan, but it can also tie into a company. It can tie into a company saying, okay, when are we going to start making money? We've spent this much money. After this, now we're making money. All different things you can tie this into. But it's that idea of, when is the cost the same? When is it not going to make a difference? That's what you're looking for there on these. So you're looking for when they're equal. When either company would be the same amount, and I just used the keyword equal. You're going to set each company equal to the other, or each thing that you're comparing equal to the other. So now let's go ahead and look at example 2. What you're looking at here is, you need to set these equal. So you need to think about skates, skates and equipment being equal to just equipment. Okay, the other thing you need to look for is the variable. So go read the question again, and you'll be able to find your variable. How many hours must you skate? So there's your key right there. How many hours? It's asking us about hours, so that's our variable. Must you skate before the cost of buying and renting are the same? These are the key things you should have seen when you read that. As soon as you know the same, you know you're setting it equal to each other, whatever you're comparing. And then hours is what they're looking for in there. So $3.50 an hour needs to be equal to $1.50 an hour. But the $1.50 an hour has something else that needs to go with it. So stop and look and read the question again and see if you can figure out what needs to go with $1.50 an hour. hopefully you found $40, because remember, you need to buy the skates. So that's an original cost of $40. So your equation should look something like this. Skates and equipment is $3.50 an hour, which is equal to just my equipment plus buying my skates. So my $40 plus $1.50 an hour. Or you could have had $1.50 plus 40, but your H needs to be with the $1.50. Okay, now you have an equation that you need to solve for H, and you have a variable on each side. So you're just going to draw that line, and you're going to think about moving the variable over. If you want to use a decimal buster here, you can, but you need to stop and think about that 40. So if you were going to use a decimal buster here, it should be 350H equals 4,000 plus 150H. Completely up to you if you don't feel totally comfortable using decimals all the time. Or if you just like to make it easier and not deal with them. So 150, 1.50H needs to be moved over to this side. It's a positive, so I'm going to subtract it from both sides. And the main reason I didn't use a decimal buster here is because I knew these were going to be really easy numbers to subtract. So I just didn't really feel like I needed to. So I go ahead and subtract 1.50 from 3.50, and I end up with 2H equals 40. My 150H cancels on that side. Now I'm solving further for H, so I divide both sides by 2, and I get H equals 20. On a word problem, if you leave an answer like that, you're not going to get full credit. I want you to write out your answers, and I want you to tell me what you just found. H equals 20 means nothing to me unless you can tell me what you just solved. So what did you just find? And hopefully you all thought to yourselves or said out loud that you found the number of hours for when the cost would be the same for buying and renting. So at 20 hours, the cost for buying and renting is the same. And I had to squeeze that on the bottom of that page, but hopefully you had more room than me. Anything along this lines. You could have also said the cost for buying and renting is the same at 20 hours. Just something that tells me the question you answered. Now we're going to be looking at two special types of equations that you come across. You need to memorize what the two types are and what happens when you have these, because they have different answers. So the first one, example 3, asks you to solve 10 subtracting 8a equals 2 parentheses 5 subtracting 4a. So, first thing most of you probably noticed is that you have 2 here that needs to be distributed. And the reason we're distributing it and not combining here is because those aren't like terms. So I'm going to go ahead and distribute first. And I end up with 10 subtracting 8a equals 10 subtracting 8a. Some of you might already notice something here. But I'm going to continue on just so you see what happens. So now I go to the next step, which is I have variables on both sides, so I need to move one or the other over. When I go to add 8a and add 8a, I end up with a 10 equals 10, and notice that my variables canceled on both sides. Well, 10 does equal 10, doesn't it? And if I was to subtract 10 from each side, I would end up with 0 equals 0. What this is showing right here, if you noticed up here, is that you had the exact same equation twice. Just here, it needed to be multiplied out. And if you think about that in math terms, if I plug 1 in here and 1 in here, I'm going to end up with 10 minus 8, 10 minus 8. 2 equals 2. If I plugged in 4 and 4, same thing. 5 and 5, negative 2, negative 2. It's not going to matter. It never changes. So what you end up finding out is that you can plug in all real numbers when that happens. Whenever you're doing this and your variable cancels and you have something that's true there, your answer is going to be all real numbers. And what that means is every real number out there that you plug into this equation and check is going to be true. So this is called an identity. They have the same identity. So the variable cancels. And if you have trouble with this, we can work on it tomorrow. But you also have an equal answer. That's the key to this one. Did you notice that you have an answer that equals out? So you just say all real numbers are solutions. Okay, so that's an identity. Now I'm going to show you example 4. I want you to really look closely at the difference between these once we get through with example 4. Example 4 asks you to solve 6m subtracting 5 equals 7m plus 7 subtracting m. So I draw my line out of my equal sign and I check. Notice I have like terms over here that need to be combined. So first step, I'm going to combine my like terms there. So I always want these to be as simple as they can be when I look at them. So now I end up with 6m subtracting 5 equals, remember this is 7 minus 1, which is another 6m adding 7. So notice up here that once we did that, we had the exact same equation. Here we have the same coefficient and variable, but different numbers here for our constants. So I'm just going to keep following the same rule, which is now I need to get variables to one side. So I'm going to subtract 6m from both sides. I end up with a negative 5 on the left and a positive 7 on the right. Hopefully you see the difference between these two solutions here. Notice this one, 10 equals 10. So it's always going to be true no matter what. On this one, negative 5 does not equal 7. And think about it right here when we had this equation. No matter what I plug in for m, I'm going to multiply it by 6. I'm always going to have the same number here. But on this side, I'm subtracting 5. On this side, I'm adding 7. They're never going to balance out. No matter what number I plug in there, these will never balance. They're never going to equal. So in terms of that, you're going to say no real number solutions. Every time you come across that, that's what you'll do. So this is a no solution problem. We're talking about no solutions. The variable's still going to cancel. But the answer will not be equal. Or balanced. Okay, it's not going to be equal or balanced. And you answer that by saying no real number solutions. So you need to know the difference between those two types of equations that you're going to come across. And that's the end of this lesson.